Hello, chemistry. We are continuing on section 2 of chapter 22 on page 688, and we're going to talk about the properties of alkanes. Again, alkanes are hydrocarbons, that's carbon and hydrogen, that have all single bonds. In this table, it is comparing straight chain alkanes, that means one right after the other, in a straight row, no branching. And it shows you the boiling point. This means that methane will boil at a very cold temperature, almost the same temperature as liquid nitrogen. It's much safer to play with liquid nitrogen because it's not flammable. Methane is very flammable and explosive. Ethane, propane, which is what is in those a lot of people have in their houses for stoves and so forth. Butane. Sometimes you might even find they make curling irons that use butane. That's lighters and so forth use butane. Pentane, octane starts to be the size of molecules that's in gasoline. That's why it's got an octane rating. And you notice here we're minus 164. Octane is already 125 degrees before it boils. Water boils at a lower temperature. Decane, heptadecane, and I'm not even sure I can say that one. That's 20 carbons. And you have to get to 343 degrees to get that to boil. At room temperature, it's a solid. These are liquids, and these are gases. Now, what's the properties based on? Well, the longer and longer the chains get, the more chance we have for London dispersion forces. We've talked about those before. So that if you have just two molecules, have very little attraction to each other. And imagine there's 4 hydrogens on here, but there's still non-polar bonding, and so it doesn't have much of an attraction. If we can get some chains going, these chains have more of an opportunity to get attracted by London dispersion forces, and so they will be slightly attracted and therefore more willing to form liquids or solids. So the longer the chain is, the more London dispersion forces, the higher the boiling point or higher the melting point of the molecules. So this is what's discussed here on the top of this page, 689. Natural gas is a fossil fuel composed primarily of alkanes containing 1 to 4 carbon atoms. So the gas that we're using to burn to heat our houses and our classroom and so forth is made of 1 to 4 hydrocarbons. If we get a little bit bigger, they're going to be liquids, and larger yet are solids. So candles are huge hydrocarbons, and they make solids at room temperature. Now, an application to life is, how do we get gasoline for your car or diesel for your vehicle, or jet fuel, or these different motor oil? How do we get that out of what we get out of the ground? When they pump oil, as it's called, out of the ground, or petroleum is the fancier name, a complex mixture of different hydrocarbons that vary greatly in composition. They can be from 1 carbon to 50 carbons, all in the same barrel. Well, we can't really use it very well in that form. So they put it through a process called fractional distillation. And basically what happens is they make a huge tower, and I'm not much of an artist, but let's say we make this huge tower. And the bottom of this tower, we have oil in here. We put the oil from the ground into here. And then we heat it up. Make this super hot. Your book says about 370 degrees Celsius. We make it really hot. At that temperature, almost all of it will evaporate. And what they do is they cool it down to where it's really cold up at the top and it's hot at the bottom. So as the oil evaporates, the big molecules, they will condense very early. So they will go off to the side here, and this will be maybe oil. Keep on going up, and a little large, not quite as big as oil, but still big. We get diesel. And then we get gasoline. Until finally we get to the top, and we are getting natural gas. And this is how we can separate one barrel of oil into all the different fuels that we need. And there's many of them that come off of here depending on what? Their molecular size and therefore their boiling point. And that's how fractional distillation works. So what do these molecules have in common? What they have in common is a double bond. Now, not all double bonds. In both molecules, you see they have single bonds, but they have double bonds. So in our book, on page 690, we start talking about unsaturated hydrocarbons. Unsaturated meaning that there is a double bond. Doesn't have to be all double bonds. In fact, most of them are not double bonds. But it has to have at least one double bond, and if it's or triple bond. If it's not all single bonds, then it is unsaturated. This molecule here is saturated, no double bonds. So molecules that have double bonds in them are called alkenes. Alkanes, spelled with an A, is for single bonds only. If it has a double bond in it, then it is a alkene. In a few moments, we're going to talk about alkynes. So many times students ask me, does it matter the spelling? Well, sometimes more or less, but in this time, it does matter. You've got to get that one letter right. It's either an E or an A or a Y. Now, if it has just one double bond, then the general formula for it is H2N. You might remember that for the alkanes, it was 2N plus 2. But this is only true if it has only one double bond. If it has more than that, then this formula doesn't work. As mentioned before, we can have two different kinds of isomers. They're geometric isomers. We can have the cis isomer, where the functional groups are on the same side of the double bond, or we can have trans, where they're on opposite sides of that double bond. Here's a table that shows you some of the naming. Again, if you have two carbons, it's going to be eth. But instead of calling it ethane, a molecule that has a double bond in it becomes ethene. Propene. Here is trans-2-butene. Notice butene is 1, 2, 3, 4. Cis-2-butene is 1, 2, 3, 4 this way. And what does the number 2 tell us? That means that the double bond starts on the second carbon. Now we need to talk about some naming. On the bottom of page 691, it says that we're going to name the parent carbon according to the longest continuous chain. Longest continuous chain. Well, that gets a little more tricky because it has to contain the double bond. It has to contain the double bond. Now, let's take a look at the example in your book right here. They show this molecule that has 1, 2, 3, then double bonded CH2. I'm drawing it slightly differently. 1, 2, 3, 4, 5, 6. Okay. So there's 6 in a row, and then there's a double bond here. And it would be very tempting to call it hexene. But we have to include the double bond in the longest chain. So really, we have to do it, which is longer, 1, 2, 3, 4, or 1, 2, 3, 4, 5. We're going to have to go 5. Well, what about these guys? Well, they're going to come down like this. And even though this is the longest chain, we have to do the longest chain that includes the double bond. So the base name for this guy is going to be pent, because it's 5, and it's got a double bond, so we're going to put an E and E, pentene. The name is not done yet, because we'll talk about this more, but if there's more than one double bond, we will modify the suffix to indicate the number of double bonds. For example, if we have 2 in there, if we had 2 double bonds in here, we would go pentadiene. So we would throw in there this prefix to say, well, how many enes, how many double bonds do we have? We have 2. And in front of that, we would have to put the numbers of where they are. 2, 2, or 2, 4, pentadiene, to name where those double bonds are. Then we have to add the names of the alkyl groups, as we did before, and you might remember that we have to do it alphabetically. In this case, we only have one group, and that is a ethyl. So this is going to be, this double bond starts on the first carbon. So we're going to say 1-pentadiene. Pentene. But we have an ethyl that we need to put on there, so we're going to call this ethyl, put a dash there, ethyl pentene. But we also have to say, where is this ethyl? This ethyl is on the, we always have to use the lowest number. We could count here 1, 2, 3, 4, 5, but it's much lower number to say 1, 2, 3, 4, 5 like this, so that we get 1 pentene and 2 ethyl pentene. So 2 tells us where the ethyl is attached. 1 tells us where the double bond is attached on that first carbon. Why wouldn't we call it 2-pentene? Because we always start with the lowest number possible for that. They give us also the example that, well, what if we had 2 double bonds here? Well, we would put the pentadiene, and we'd have to say where it starts, on the first carbon and on the fourth carbon. So it's 1, 4, pentadiene. So this is where it talks about numbering the carbons, so you get the lowest number. And we insert position numbers as we have before. And then we get to punctuate with commas and dashes. Okay, now we're going to take the next step and look at triple bonds. Triple bonds. Alkynes with a Y in it. No double bonds, no triple bonds, it's anes. Double bonds, it's enes, and triple bonds, it's ines. So we have ethane, ethene, and ethine. All right, so what's common about all 3 of these? They all have 2 carbons. This is ethane, all single bonds. This is ethene, double bond. And this is ethine, because it's got a triple bond. You can see all 3 of them here at the bottom of the page. You have ethane, ethene, and ethine. Now, ethine has also got a common name, and you should know that, and its common name is acetylene. If you were to talk about a general formula, if it has only one double bond, then it would be CnH2n minus 2, because it has 2 less hydrogens than it otherwise would be. So that's similar now in the naming system to how we did double bonds. So we're going to find the longest continuous chain that has the triple bond. we're going to end it with "-ine", and if there's more than one, we go diene or triene, and so on. So let's do a quick example. So the book does this one where we take 1, 2, 3, so triple bond H. Now, when we go to name this, first of all, we got to find the longest chain. Easy is 1, 2, 3, 4. So this is going to be, oh, they have it 5, so I'm going to add one more. So this is going to be pent. And since there's only one, we're just going to go Y-N-E, pentine. And we have to say where it starts. Now, it's very tempting to always go left to right and go 1, 2, 3, 4, 5. But no matter which way it's drawn, we always start with the lowest number possible for the naming system. In this case, it would be 1, 2, 3, 4, 5. So this is going to be 1 pentine. To give us another example right here with 4 carbons and then a methyl group as a chain. So how are we going to name this? You can count 4 this way, or you can count 4 this way, but it's going to be 4 no matter what. So we're going to call it bute. And since it's got the triple bond, we're going to, instead of calling it ane or ene, it's going to be ine. And then what's attached to it is a, so I need to say what carbon it is. 1, 2, 3, 4. So it's going to be 1 butine. And then we're going to put a methyl group on here. Methyl. And where's the methyl? It's going to be on the 1, 2, 3. So 3 methyl, 1 butine. 3 is where the methyl group's attached. 1 is where the triple bond is attached. And so the naming goes along the same lines as did the hexene and the hexanes. And the last part of our section is about aromatic hydrocarbons. These are carbons that have 6-membered carbon rings, and they have delocalized electrons. Benzene is the primary aromatic hydrocarbon. So let's do a little quick review. What would this guy be called? He's got 1, 2, 3, 4, 5, 6. So it'd be hexane. All double bonds. All single bonds. So no double bonds. It's ending in ane in its name. And we call it a straight chain even though it does this zigzag pattern. Now, what do we call it if we were to take off a hydrogen off of this end and a hydrogen off of this end and then put it together end to end? That would be a cyclohexane. 6 carbons in a ring. Now what we can also do is we can actually take off 6 of the carbons and we can form this guy. So we took off 6 of the carbons and now we have a double bond on every other carbon, or every other bond is a double bond. That is benzene. Benzene is very important. That's why they mention it in particular. It is got so many things that can be attached to it, and it plays a role in a lot of things that you can smell, and perhaps that's why they call it aromatic. And even though we make it with double bonds here, the truth is there's no more reason to have a single bond here and a double bond here than to have it the other way around. And what actually happens in reality is that the double bond electrons are actually free flowing around this ring, and that's what they're trying to show you right here, is the delocalized electrons allowed to travel around this ring. And we can even take off a hydrogen and replace it with a alkyl group, and you can see here what was attached was a methyl group, so this would be methyl benzene. You notice that sometimes they don't even bother putting the number there, because if there's only one methyl group, by definition, wherever it is, that is carbon number 1. Now, what if we wanted to put another one on there? we could put it, say, right here. Now what do we have? Well, now we have to start saying numbers. And in this case, it doesn't matter which one we call number 1. We could call this 1, 3, 1, 2, 3, 1, 3 dimethylbenzene. 1, 3 dimethylbenzene. And we can continue to add things, ethyls, whatever, to this ring and name it accordingly. All right, the last thing to point out here on this section is that all 3 of these different ways of drawing are correct and the same. Here we're showing single, double, single, double, single, double with the H's around there. Well, really, since these are delocalized electrons, they're not really double, single, they're flowing around. So to show that better and also probably be a little lazy instead of drawing 3 different lines is just to draw a circle in the middle, and that is to suggest that the electrons are going around. So this drawing and this drawing are the same. And since we all know that there are these hydrogens sticking out, we get even lazier and we say, okay, just know that there's a hydrogen sticking out here, and they draw a hexagon with a circle in the middle. And that is representing that molecule, same as that is. And here is that benzene ring drawn with a methyl group on it. All right, that concludes our section 22-2.